stealing is thunder, is an exercise which began about 3 years ago towards the development of a test standard. And this is basically the story of that standard. For those of you familiar with who work in fracture mechanics, we know about fatigue threshold. The fatigue limit in smooth samples and notch samples, and we also know that it depends on mean stress. Dr. Sunder has, I think, for the last 20 years, been arguing that a similar argument should apply for the case of ΔK, that is the fatigue stress intensity factor amplitude threshold. And this is the story of that exercise. So I will leave Sunder to start his presentation.
Hey, thank you, Vikram. And I think you've done about half of my presentation already. With that, you put in a nutshell what I would probably take an hour to explain. Thank you. I'll have to share my screen.
Yeah, Sunder, can you check once if you're able to? I've made you a presenter, so it should work.
Yeah.
Yes.
It does? Okay. Thank you. Good evening, everyone. And I'm very sorry about this delay.
Sunder, if I may, there's a tiny bit of noise in your speaker. If you want to check that once.
What I can do is I can just use the microphone on the computer. Just tell me if that works better.
You could give it a try once, yeah.
I think it's better he doesn't tinker with anything. Seems to be very sensitive.
Yeah, maybe I made a, yeah. I don't know what happened. It says on hold. So he's not out of the link, but sorry, give us 2 more minutes. Yeah, can you share your screen again and mute yourself? I don't know why. Okay, now I can see him unmuted. Sundar, can you hear us?
I can hear you.
Okay,
but I can hear you on the mobile.
Yeah, we can. Oh, are you on your mobile?
Yeah, now I can hear you on my system as well. And I'm going to share my screen.
Yeah.
Please tell me when you can see my
Yes.
screen so I can
Yes.
continue.
Yes. All
Yes,
clear.
please go ahead.
Yeah, thanks.
Thank you. Okay, let me not waste any more time and hope that I don't get removed from the meeting. On this first slide, I'm trying to show you on the vertical axis on these plots how a load spectrum looks in real life for say an aircraft wing, the kind of loads you see on the on the graph over here. It turns out that most of the damage is actually caused by small cycles. You can see this is the damage curve, and that is the load exceedance curve, and they the last 10% of the amplitudes, the smallest amplitudes of cycles, they cause 80 to 90% of the damage. The same thing for helicopters, and I would imagine it applies to a lot of vehicles that move, rotate. So it turns out that small load cycles matter a lot. And if you look at how the fatigue crack growth curve looks, where the vertical axis here is the growth rate and the horizontal axis is delta K, the lower growth rates probably matter most, right? If most of the fatigue life is spent due to crack growth rate at low rates because of a small crack size, or because most of the load cycles that push the crack forward are actually quite small in service. But if you look at these two plots, and it would apply to most plots that you would see in the literature, there's a lot of scatter on the delta K threshold. That is the lowest delta K at which a crack will start growing, which is associated with 10 to the power of minus 7 millimeters per cycle. And that is because this property, delta K threshold, is very sensitive to how it is determined. Now, in life, you can't be very comfortable with a property that depends on how you measure it, right? You want a consistent way of measuring it. But even my colleagues at ASTM, with whom we have discussed this quite a lot, they actually say that the prevailing standard, the ASTM E3490 and its equivalents in ISO, they don't focus on threshold. They focus on the intermediate range of crack growth rates, which are used quite a lot in engineering application, but they're used for other purposes, not for the purpose of determining safety or life between inspections or even total life. They're used also extensively by people in research simply because you can finish your experiments quickly, right, when the crack grows fast. You don't want to get down there and spend weeks trying to get a result, and particularly with our power shutdowns and things like that. So in any case, the story is that the delta K threshold is very sensitive to how you measure it. But there is a more important thing. And the more important thing is that delta K threshold actually consists of two parts. That is not even recognized by prevailing standards. One part is associated with crack closure, particularly as the stress ratio at which you determine threshold comes down below 0.6, 0.5. The crack begins to close under tensile loads, and that affects how the measured value of delta K threshold. And unfortunately, that is sensitive to how you do the test. There is the other part, which is the intrinsic threshold, which is a subject of controversy, because the fracture mechanics community, it has two two parts. The crack closure community, which is very loyal to the concept of crack closure, it believes that intrinsic ΔK threshold is actually a material constant, and that it can even be theoretically determined from dislocation dynamics, depending on modulus and parameters like that. The rest of the community doesn't believe in crack closure anyway, or treats it as an unreliable and inconsistent phenomenon. And it just correlates ΔK threshold, the sum of the two. Now, the new standard, looking ahead, E3490, which Vikram introduced very nicely in the beginning, it determines the intrinsic component. And it turns out that the intrinsic component is very sensitive to a near-tip stress parameter, which is plotted here along the horizontal axis. And you can see along the vertical axis that ΔK threshold intrinsic can change quite a bit depending on this computed value of near-tip residual stress. And this is the plot that ASTM E3490 helps you determine. It specifies a reproducible, highly reproducible test method to obtain this relationship. Now, this relationship can be analytically, purely based on equations. It can be translated into ΔK threshold intrinsic versus crack opening stress ratio. Now, what is crack opening stress ratio? You can treat it as the stress ratio if there is no closure. So this will apply to initial defects. And if you want to look at long cracks, you look at the plot at the right, and you can see that the total ΔK threshold will be the sum of the closure component. Now the closure component is given by the shaded area, which is sensitive to how you perform the test, and the intrinsic component, which is over here. So from these plots, you can see that the intrinsic threshold is not a constant. It's a property that is sensitive to near-tip residual stress. So as Vikram pointed out in the beginning, it is mean stress sensitive. And the second thing is, because we know how to determine it, we can also see how wrong we are in applying prevailing test methods to determine threshold. And these are actual data points that I've shown over here, which we obtained on a 15 millimeter thick naval steel, low alloy steel, using compact tension specimens, regular specimens, which are with the whole circles over here, and the open circles. They show the readouts we got from compact tension specimens with side grooving. So when you do side grooving, you're imposing plane strain conditions and you're reducing the extent of crack closure. So that's what you get. But actually, the intrinsic threshold is the value that you should get, including the closure component, if it was a closure level that you see in long cracks under non-threshold conditions. So if you take those conditions, this is what you should get. So what this implies is that when a crack is growing naturally, this is going to be the curve it will follow. This is the property it will follow as a function of applied stress ratio. So the new standard actually helps you get more realistic or treat it as conservative values than what you would get using prevailing methods. And once you get the intrinsic threshold, if you have legacy data, there are hundreds of data points available from previous experiments. From those, with knowing this relationship, you can extract what was the closure component. At least you will find out how wrong we were in determining it the old way. This relationship becomes even more important under service loading, because when you have a load history the crack tip is going to see variations in local stress, because of stress strain hysteresis. And because of that, on a cycle by cycle basis, it's going to see a different threshold. So that is the margin of variation you can expect in intrinsic threshold if you look at real service load spectra for different structures. And I'm really happy that we finally have a test method which addresses a practical issue of service spectrum loading. So this is the first standard to determine a material property that is sensitive to load history, and it can be modeled. Now let's look at the science. How did we get there? Because this is about history. Many years ago, about 25 years ago, we were doing an experiment on natural crack formation at the notch root. And we used a load sequence that is shown over here. We wanted to see whether there is a mean stress effect when there is no crack closure. And we were surprised that in a naturally forming crack, now that is a notch root, that is a particulate near the notch root from where the crack took off. And you can see that initially, as the crack grows, the crack extension in that step, the first step of 2000 cycles, is much more than the crack extension in this step. But as the crack grows larger and it becomes a long crack, the crack extension in all three is identical. So we drew the wrong conclusion that this is a small crack effect. And you'll find a lot of such papers in the literature called small crack effect. So it turns out if the crack is small, the effect will be there. When the crack gets large, it won't be there. And then one fine day, looking at the same fracture surface, but into one of the cavities left behind by a secondary particulate, I was shocked to find that the concentric rings, which show the progress of an interfacial crack that was separating the particulate from the matrix in the same aluminum alloy, that was showing a constant growth rate in all three steps. Now, this is an extremely small crack, This is probably the smallest crack any of us has seen. It's about 120 nanometers in diameter. And it's growing at a constant rate, independent of the applied stress ratio. This is in the same material, same specimen, in fact, but it's a small crack which is not seeing the effect. And I came to what at that time seemed a preposterous conclusion, that perhaps it's the environment. After all, the secondary particulate was getting separated in high vacuum, right? This is the Janta vacuum where you don't have to spend a lot of money on a vacuum chamber. You just grow a crack around a particulate and you'll have ideal vacuum conditions because the particulate is sitting in front of the crack front. It's not been cracked yet. We got to see it after the main crack went through it. I spoke to my colleague there, John Porter. I consider him a wizard in terms of being a microscopist. And I asked him, hey, John, can you just confirm that we are looking at what really happened and not some kind of an artifact? And within minutes, he pulled up the same cavity on the opposite fracture surface. So here you can see the mirror image, but rotated, reversed so that you can compare easily. And you can see that both fracture surfaces, we are looking at exactly the same spot. And there's the particulate that came off. So we were looking at something real. And the possibility that it was really vacuum that played the trick. So after a lot of, shall we call it PR and administrative effort, I was able to get on to high vacuum test machine, a test system at the Air Force Research Lab in the US. And we did a test on a notched coupon, applying a number of blocks in air and then evacuating the chamber and going back and repeating another n blocks in high vacuum. And we had to wait 2 days to get 10 to the power of minus 8 torr vacuum, because my other colleague, Andrew Rosenberger, who afterwards really helped with the standard itself, he said that anything less than 10 to the power of minus 8 will not do. There will always be even a ppm level of moisture is good enough to cause an environmental effect. But the net result is here to see. This test took almost a month. But at the end of that, when we looked at the fracture surface, here you can see that is the growth in air from left to right. And then when we switch to vacuum, you can see the crack extension is identical in the 3 steps. And this is at an earlier stage when the crack was smaller. In high vacuum, equally spaced steps. So it turned out we made a discovery. And that is that the mean stress effect, one of the main reasons for the mean stress effect is actually the environment. And if you come to think of it, isn't it logical? After all, when the atomic spacing is closer to each other, it's not going to allow diffusion. It's not going to allow diffusion of active species, right? Because it's like putting a coat of paint and not allowing the environment to attack the surface. And mean stress plays that role by controlling the spacing on the surface of atoms. So surface diffusion of hydrogen released when a metal oxide is formed is probably why we see the mean stress effect in fatigue. So it's one of the reasons. And till now, there was no known reason for the mean stress effect, and I'm glad that we cracked that that observation. Well, it's just 160 years after the mean stress effect was established, after all. So if you have a mean stress effect on a notch, this was established in a very innovative, beautiful experiment performed by Jodine Morrow and his student Stadnik back in the early 1970s, where they applied a prior load to induce residual stresses at the notch root. And then they found that the fatigue life depended greatly on whether they went down first or up first, because that way you're reversing the residual stresses at the notch root. So that is the history effect. And it becomes predominant as your life goes higher and higher towards the endurance limit, which means that it's the fatigue limit that is affected. And amazingly, they also laid the foundation with this experiment for notch fatigue analysis, because they showed that you can take a smooth specimen and apply the same stress strain history, and it will show you the same effect. That's why the data points from smooth specimens and notch coupons are shown on the same plot. And that is the graphic representation of what happens to the mean stress when you apply an overload. So it turns out hysteresis is the culprit. It's hysteresis on the stress strain response, which is responsible for both the mean stress effect as well as the load history effect. Now, you can look at a notch root, but you can also look at the crack tip. So here's the notch root. The local stress is given by stress into stress concentration factor. That's a local elastic stress. But I can also look at the crack tip at some distance from the crack tip, and I'll get the elastic stress at that point through this equation. So this was the starting point, shall we say, of how this ASTM E3490 took off. So this happened probably 2008, 2010. So I wrote these equations for a crack tip. And then the work started. So it turned out that there's a certain near-tip stress which probably moderates near-threshold crack growth rate. That stress should be controlled by applied stress ratio and load history. So I derived the equations for what happens when you have a load history. That is an overload, an underload, followed by the baseline cycling. So I'm determining threshold under the baseline cycling, but I can periodically apply these overloads and underloads to punch in a desired near-tip residual stress. So that's how an elementary load sequence was designed to simulate load history. Then the equations came up, and then a test method had to be developed to implement this in a reproducible way. So this is the load sequence that was used, and it is now part of the standard. And the first results were published in 2013. Between 2013 and 2020, we exercised this method on more than a dozen materials, published a lot of papers on them. They all showed highly reproducible relationships between threshold and near-tip residual stress. We even were able to show that non-heat treated additively manufactured material with residual stresses produced during the additive manufacturing had an impact on the plot. They just shifted the plot. So when you do something like that in additive manufacturing, it attracts the attention of the community. Then 10 years after the publication came the idea that we should do a round robin. There is a very important political reason for this, which I should share with you. And that is that, typically a lot of research is done and a method is published in papers. And then people agree that it's a worthwhile method, like, method for low cycle fatigue testing or for a tensile test. And then somebody writes up the test method and people are familiar with that. Everybody who comes to the meeting is aware of it. So therefore, when you submit that as a standard, the consideration of that is taken, in a very understanding manner. But here we have a test method that was made in India. And imagine going with a test method to a body like the ASTM and telling them, we want you to consider this as a standard. It would be looked at with some skepticism. Therefore, I believe we did the right thing in first doing an interlaboratory study. And we involved 14 labs. And I would say the credit for all this should go to the Indian Structural Integrity Society, and I had tremendous support from colleagues over there. Vikram is here at the meeting, and he can probably present a talk just on how this whole thing was done. We were very lucky to get support from DMRL, who provided the material. And as many as 10 labs in India, again, one could talk about it for hours, got involved with this work. 3 labs in Russia agreed to participate in the program, and have to mention a very important participant in the form of the Air Force lab in the US. And they have a vested interest in this because this concerns aero engine materials quite a bit, because they are very sensitive to threshold properties. So this is how, all these circles indicate where these 14 labs were. I must express my deep appreciation for the support I got from my own company, from my colleagues in my lab at BISS. They did all the coordination. Vishwas is here at the meeting. He was the one who would collect all the data from the different labs. And this whole effort was, it was done at an amazing pace. So we set up a schedule. We did 3 workshops within INSYS with the participation of the round robin participants. And the work started
I think specimens were distributed in June, July of 2023. And by March of 2024, all the results were coming in. In April, I think the report was submitted to ASTM. It was registered as an ASTM interlaboratory study. And the lady over there was kind of perplexed because she couldn't assign a number to the report. She said, first we need the standard. Only when the standard is there, we can publish this report. Anyway, today it's a publication. So the net result of that interlaboratory study was that we got these, almost 700 points, which you can see here in a very narrow scatter band of standard deviation of 7% or less on all three materials, 2 aluminum alloys and low alloy steel. Don't forget these were threshold tests. So each data point would take about 2 to 3 million cycles to get. So you can estimate from these number of data points that almost between 15 and 20,000 hours of testing was involved among the 14 labs, which was a tremendous, tremendous example of outstanding voluntary effort. Nobody got paid for it. So what is the importance of this standard? Now that we have a standard test method, there are several things that I'd like to mention here. Number one, it allows us now to apply in real engineering, solving engineering problems, the relationship that we now have. We can use this to plot a diagram which Kitagawa and Takahashi invented, but they would never have imagined that the same diagram can be used for design purposes, not for constant amplitude loading as they envisaged, but for a load spectrum. And a paper has already been published in ASTM about how to use these data to construct a Kitagawa-Takahashi diagram to support design for safe life and period between inspections. Essentially, this is on the vertical axis, you have the design stress for a structural element. On the horizontal axis, you have initial defect size. So depending on the defect size, your design stress level will have to be brought down for a finite life, service life. But if you're looking at inspection period, as long as you can detect a defect of this given size, you can increase the inspection period. And this is a key element in maintenance on condition. This makes sense for the person who is procuring the non-destructive inspection equipment. This makes sense to the design engineer who writes down the technology and allowable defects. This makes sense to the quality control person who receives material at the stores. So it's a very valuable addition that we can make with this new property. Obviously, with the way threshold was estimated using the older methods, this would not have been possible. Over here, there is this is a table which I pulled out of the mill handbook for engines. For aero engines, the allowable defects are in the range of 0.3 to 0.7 millimeters. Now, if you look at the size of a defect as a function of ΔK threshold and the applied stress amplitude, you will see that the defect size is a function of the square of ΔK threshold. What that means is the way you determine ΔK threshold is going to impact this value in a parabolic fashion. That is enough to underscore the importance of getting real material properties rather than properties which are obtained by a method which affects the result. But let me come to something more exciting to me as a researcher. This picture on the screen here, you can see from the date, it was first published in 1967. It's a fantastic picture obtained using a transmission electron microscope. You can see the effect of shadowing on the quality of the contrast. But I'd like to draw your attention to the load sequence. You have baseline cycling and then 3 cycles at a slightly reduced stress ratio and then back to the baseline cycling. And look at what that causes. This is the baseline cycling. The crack is growing from the bottom to the top. And then those 3 cycles, they're just growing at half the rate of the baseline, but they have the same range. And the change in stress ratio is very marginal. And these load levels are above crack opening load level, which is confirmed fractographically. So what is it that caused that change? Nobody has been able to explain. Macmillan and Pellow, in their original work, they said it had to do with the crack tip sharpening and blunting. But that model is discredited because it doesn't explain the other things you see over here. One of the other things you see over here is this jump in crack size when the load goes up from here to there. The load has just gone up by about 28%. But the jump in crack size in the crack front is huge. Without going into the details, I can tell you that using the properties you get with ASTM E3490, you would be able to explain all these 3 interesting features you see on the fractogram. In other words, this property allows you to develop variable amplitude models of crack growth, which are microscopically consistent. And there are several papers that have been published in this regard, which show that with this property, you can model crack growth along with crack closure in a way that you can computer generate this fractograph and it'll match 1-to-1, at least qualitatively, with what you see here on this old picture. So I'm really happy that we were able to do this. But I must also mention that very few people do such research involving specially designed load sequences, programmed load sequences. That is not in the manner of things. 99% of the experiments in fatigue are conducted under constant amplitude loading. And I'm sorry to say that is very, very far from what is required in engineering practice. It's, doing research on variable amplitude fatigue, it demands flexibility in designing a fatigue test. And I'm really happy that I started my career in NA, where back even in the early 80s, the emphasis was on understanding what happens under variable amplitude fatigue. So I remember that I was very frustrated with what was available then as test equipment. So now I'm just getting into the roots of what made me jump into this and get where we are right now. So I was in the early 80s already thinking about variable amplitude loading, and it's that kind of loading you see which is part of this method. But if you buy a testing machine today from most commercial suppliers, you wouldn't be able to do a test like this. So this requires dedicated software, which means you need a computer-controlled testing machine, and you need the ability to program such loads. Otherwise, you can't do that. But the salesperson who comes to sell you the machine is invariably going to reel off all the standards for tensile tests, for low cycle fatigue, for E647, and tell you that it can do those tests. But as a researcher, you want to be able to do something different. And that, for me, came as a blessing thanks to the consideration that my then boss, Dr. Valluri, late Dr. Valluri, he agreed to somehow scrape up 3 lakhs of rupees and said, okay, here's the money, now you see what you can do with it. And that was when we developed our first controller for testing machines, in which we could program any load sequence back then. And at an ASTM meeting in 1990, that was deeply appreciated so much that the picture of our board made it to the cover of the special technical publication from ASTM. And that controller had a mnemonic programming language which allowed you to program any load sequence that you wanted. So I was just thinking, where it all started, and I believe it started those years. And now, with the company that started in the early 90s, we've been able to do a lot of things. I developed a lot of test systems. Here I put a picture of our team. I like to believe very strongly that they made this standard possible too in their own way, because we've been able to build a huge variety of machines. Our equipment is used to test the escalators for the Moscow metro, for example, the wheels that go on the trains. It's used to test turbofan blades in 3 axes. And all these customers, they want the ability to have programmed load sequences. So that tells the entire story from when it began. But now I'd like to look at the future. And you'll be very happy to know this is the last slide. So will this standard make a difference? I've been discussing this, to get the standard through a committee with more than 200 members, where even one negative vote would hold back the standard. It's a standard built by consensus. It was a lot of effort. I must have attended at least half a dozen ASTM meetings to talk about the standard, the problems, the round robin studies that we did, and so on. So what now? It turns out that the challenges only begin now. If we want this standard to be used, we have to deal with ground realities. What are the ground realities? For almost 5 decades, engineers around the world are using commercially available software with codes like AFGROW, NASGROW, FastRun, and so on. Those codes don't use these properties. So we now have to show through publications, and there already are about more than 15 publications, I think, but many more are required to get people to realize the difference the standard makes. That is why we are going to do workshops. At the SAIS 2026, we'll be doing a workshop on the standard. We have to do more research studies. We have already shown that it works very well for elevated temperature crack growth in nickel-based superalloys. And it's also a question of negotiations. We have to deal with the people who develop, update, and support these codes and make sure that they have an interest in that. And for them to have an interest, we have to get the industry to demand this from them. That is why I see myself at least busier than I was in developing the standard. So if any of you is interested in working on papers, on PhD theses, on research related to the application of this standard, I'd say go for it, and you will have the support that you need from the society. INSYS, I'm sure colleagues at ASTM will be willing to help. They've already pulled me on board for the ASIP meeting in the US in November, where we'll be talking about this. the ASTM has a committee on structural applications, and the chairman of that committee has asked me to come and present a talk on how the new standard will help lifing for structures. So we have a lot of ready-made material that can be presented over there. So, as in the market, we have to do some marketing, but with a very technical background. Thank you very much for the time. I hope I haven't overdone the time part, and I'm sorry for the delay in starting this talk. If there are any questions, I'll be delighted to address them, and comments, particularly critical comments.
Thank you, Sunder. Thank you. That was lovely. You actually didn't take much time at all. You started 15 minutes late and you've finished 10 minutes early. So we have plenty of time for questions. I think I'll just request people to unmute themselves and ask, or raise your hand and I can call you out. I don't see anything in the chat box. So.
So, can I ask a question? This is
Yes,
Mangalgiri
please.
here.
Yeah.
Yes, Prakash. Sure.
Yeah, so very interesting. Okay. And so, as you mentioned on the last slide, one of the things to show the usefulness would be to say, if you do the standard way, like if I take the Falstaff spectrum for aircraft, do the standard way of crack growth, and do it the way now that the new standard projecting new properties, how much difference it would make in terms of estimation of life or estimation of inspection periods? I think.
Well, your question is a little bit deflating for me because you mentioned the Falstaff load spectrum. In the Falstaff load spectrum, you can throw out 95% of the load cycles from the spectrum. Just the 5% of the cycles will give you the same result in crack growth. Therefore,
but let's say we don't throw it. We don't throw the. I mean, that is what we want to impress, right? I mean, that the load cycles which we are throwing out are going to make the difference.
True, they will make a difference if they are there in sufficient number to contribute to damage. So the Falstaff load spectrum is probably not the best example. If you take the twist load spectrum, where most of the load cycles are due to gusts, and gusts come from turbulence. So, if you look at the gust statistics, when the load gust amplitude comes down by half, the number of cycles at that lower amplitude goes up by a factor of 10. Okay. Therefore, the smaller and smaller cycles actually will keep exponentially increasing in number. Whereas for a fighter aircraft, the Falstaff spectrum is for a fighter aircraft. For fighter aircraft, the loads are mainly from maneuvers. Turbulence doesn't make a dent, on a fighter aircraft. So, but if you look at helicopters, it makes a huge difference. Rotary
so maybe identify a couple of standard kind of cases where we can show what difference it would make to this, particularly in airlines.
That has already been done for a twist. It has already been done, Prakash. There's a publication on that. Yeah, it makes a huge difference. About factor
would it
of
make?
4.
So let's say some designer is using a standard method, like Willenborg method or Wheeler method for taking cycle by cycle crack growth. Okay. So correspondingly, something like that, would there be some kind of a standard method for a designer to use in order to estimate some cycle by cycle growth?
It's an important point you make, and I mentioned that only in passing because AFGROW actually uses the corrected Willenborg model. Now, what happens is both the AFGROW and the Wheeler models, they use empirical constants. Okay, to look to correct for low history effects. With those empirical constants are obtained from trial tests under spectrum loading under the same spectrum. Now, with this material property, you don't need any fudge constants. You can determine the property because the property reflects low history effect. And this is a property which is accounted for using 100% applied mechanics equations. So there's zero empirical connection over here. Once you have the constants from the method from E3490, you don't need to do any more correlative testing. And the important thing is the people who developed AVGRO, NASGRO, they can incorporate the new property without messing around too much with the code. It's possible. Yeah. So that's a bright side. Yeah.
So I think it will be a competition between how much effort is required in terms of establishing the current level of fudge factors. The current fudge factors are obtained from test data anyway. So how much effort is required to produce that test data as compared to how much effort is required to obtain these 3490, those threshold properties.
Right.
Okay. So
the pipe dream will be to have these properties make their way into the handbooks, right?
Right. Yeah. Of course. Very nice. Very great. Thank you.
Yeah, Jaya, go ahead.
Yeah, thank you, Sunder, for this. The first time that I'm hearing you talk about this standard. Maybe I've missed this. I mean, you did talk about threshold stability factor calculations many of your presentations. But I had one question about this particular graphs that you have put up in your last slide. If I take the example of managing steel versus PH1 steel, maybe the precipitation hardness steels, the behavior is quite different. Like in some cases, there are like two regimes where it's very sensitive and then it becomes a plateau. And in the case of managing steel, it seems to have not reached a plateau or it's just does not exist. Is there any reason why this is the case?
Well, if you look at most materials, they do have a plateau. Okay,
right.
that's the
yes.
they kind of flatten out towards the
yes.
One exception is titanium, because in titanium, as you keep pushing the near-tip residual stress to the right, you start getting the time-dependent effect, because titanium creeps at room temperature. So that's what comes in the way for titanium. As far as this managing steel is concerned, these were miniature specimens, Jaya. You can see there are hardly 4 or 5 data points over here.
Data points,
My suspicion is that we haven't gone far enough on the right-hand side.
Oh. And the reason
how about aluminum alloys?
Aluminum alloys, they have a plateau. Here's 2024.
I think you had shown
that is
earlier
70,
slides.
75. Yeah. They have a plateau.
And you said something about being able to analytically model this. So is there a way where you can model where it plateaus? And also the reason that it's sensitive in the negative stress regime is because of your crack closure stresses, is it? Is it more sensitive in the compressive regime?
I don't believe at this point of time one can model this curve. But you can use this curve to model how the crack will grow under a given load spectrum. That's what you can model, because there you're basically using applied mechanics equations. No, there's no fudge element over there. And for each load cycle, you are computing what is the sigma star, that is a near-tip residual stress, and picking off the ΔK threshold associated with that and plugging it into your growth rate equation. That's what you do for each cycle. Okay, so that you can modulate, and it doesn't depend on the material as long as you have this property. The other good thing about this property is that we haven't seen a huge difference on the 7075. We did this work with Vikram, Praveen, and their PhD students some time back. We had a 7075 plate, 50 mm thick, and we found the properties on that one, and then sliced it to get just 5 millimeters, and again found the properties, and they were kind of more or less one and the same, which is not what you will find with crack closure, because crack closure is sensitive to stress state. Whereas here you're sensitive to stress state, but under threshold conditions, for most of the crack front, you actually have a plane strain condition. Therefore, the stress state remains the same. Remember also that you determine the stress strain curve, which is an important input for this property. The cyclic stress strain curve is obtained on smooth specimens, which see plane stress conditions. But that doesn't matter because it's a mistake that is made at the system level. Therefore, it reproduces in the modeling, and that's how you get away with it. So you don't have to have the stress strain properties in for the plane strain condition. The other thing, you being a researcher, let me pose this possibility to you and your whiz kids around you. You have this relationship. It's between ΔK threshold intrinsic, which is the fatigue limit for the crack tip, and a computed near tip residual stress, right? This near tip residual stress, you can convert it into mean stress. It's just an analytical conversion. Would you then think about converting this into the Goodman diagram for the material? Don't you think that possibility exists? Then you would have a new standard to convert this property into the Goodman diagram. How about that?
Yeah, I have to think about it. but yeah, I get what you're saying. I get what you're saying. I'm just not. Is it? Yeah, I'll come back to you later. Yeah.
Okay, Dr. Brahma.
Questions.
Yeah. Good evening. Am I audible?
Yes.
Yes, Brahma. Yeah.
Okay. So it's not a comment or a query. This is a point of view from the industry perspective point of view. Since you are mentioning about AppGrow, NASGrow, and all, usually any OEM, they adapt into conservatism in their prediction. And though you have a load interaction model for the life prediction, but so far they don't consider it because their always approach is conservative. So at least they use NASGrow equations, which is developed by NASA, where it takes care of your crack closure and ΔK threshold. So far, based on your study, as we know, ΔK threshold depend only R. Now you have a closure and intrinsic. So probably that may help to refine the prediction. That is what I can see from industry point of view, because they don't want to take risk of getting into more detail into details. For example, your minus cumulative linear equation, damage accumulation. Of course, miners are also developed a non-linear equation. Of course, damage is a non-linear, but nobody talks about non-linear because that get into more efforts. But result as such doesn't make much improvement because the fatigue life itself is a lot of scatter is there. So what I can foresee that in NASGrow or AppGrow, whatever commercial software available for crack growth prediction, the ΔK threshold somewhere one can ask to come out with your findings of improvising your ΔK threshold value.
Can you please mute yourself, whoever it is? Everybody except the questioner, please mute yourselves.
Oh, I thought there was a chorus of support for Brahma.
Okay, I think that's all. That's what I want to impression, my point of view about the industry perspective point of view.
Right. I totally agree with you. Yeah. In fact, that is why any push on a standard, the push has to come from industry, even for incorporating anything new. That is why in the coming months, at least in the US, within the ASTM community, we'll be mainly talking to the industry.
There's another question. Suman, you want to go ahead?
Yes, sir. Thank you. First of all, I would like to congratulate Dr. Sunder for making a huge difference in the research community, as well as getting on with the lot of effort into this ASTM standard.
Thank you.
So Sundar, I would like to understand. I mean, maybe I am not. It's not much into this part of the metals, because my PhD thing and what I am working on with this aerospace is most often on the composites as well as the metallic side. And so with that perspective, I would like to just understand this. Now, the ΔK threshold is, yes, obviously, it is a very important one, as we see where the crack starts and where it's going to initiate. So that is of very keen interest. But apart from that, now, yes, as you mentioned previously, just one more person who was asking a question. At the threshold, we may have a plane strain condition. And as we move on with the propagation, it may turn into a plane stress condition. So a simple way I would like to put it is like, now when we have these two conditions are changing, now what is it from the industry side? What is it we should expect? Like now we should do with the plane strain in the initial stages, like, because we should have the numbers ultimately. So there, should it go with a plane strain for the crack initiation, and over the growth, should it be a plane stress? Is that the way it should be put in? Because ultimately, this may have a very good thing that it may also be turned into a something like this Hague model which we have. It can be put into a global like something like the Goodman or the Hague diagram, from which we will be able to locate a particular point. So could you give some insights into it, Sundar?
See, typically threshold conditions are associated with plane strain conditions.
Yes, yes.
And in practical problems, if you're looking at initial defects, you just have to assume plane strain conditions, because the defect is very highly localized, and unless it's a surface defect. If it's a surface defect at a corner, perhaps you'll have plane stress conditions. But again, it all depends on how you're going to handle it. And there is, when it comes to crack initiation, the stress state can have an opposite effect. Why? Because under plane strain conditions, you want cross yield, right?
Yes.
Your yield stress is higher. Therefore, it's less of a problem. So this is a kind of mixed bag. And
yes, absolutely.
My personal opinion is, go by the property as it is determined. Because when you're determining it, you are always determining it on a particular material thickness. So you're going to use the property for that material thickness. If you have a thick component, you don't have to worry. Just assume plane strain conditions. If it's a thin component, then you're worried about long crack behavior, because these could be structural elements. And over there, the condition of the stress state is dictated more through parameters like crack closure, because of the surface conditions that dominate. So that is likely to have a big effect. As long as you account for crack closure, you're going to first get the driving force. The driving force is K max minus K opening. So you're going to first determine K opening. Then at K opening, you're going to compute sigma star. And for that computation, you can use the equations that are readily available. They are applied mechanics. The stress state doesn't figure in them.
Yes, yes. But the well, from my from the way we are working here for this Airbus, so more often the whatever the effect of the crack closure is there is considered that when you have a negative loading, so we don't consider practically there would be a crack growth, but yes, due to the conservatism, the compressive effect or that is ignored. But still it will have an effect. So I guess this standard what is developed, it could it could throw more light on such aspects, I believe.
Definitely. And this is something that Brahma might be interested to know. This property is very sensitive to compressive loads.
Yes, absolutely.
Because of the reverse yield that takes place, your negative residual stress will drift from compression towards tension, and that will bring down the intrinsic threshold value.
Dr. Sitaram.
Okay, thank you. Thank you.
Thank you, Dr. Sunder. We had a very wonderful description of something which we had by and large assumed based on certain recommendations of designers, and we were not looking into it much, but it's really something extraordinary, especially at the stress conditions where we shield with a lot of heat treatment and a lot of coatings. And then finally, the fact that the compressive loads will turn into tensile. Okay, these points I think we have not looked into all these days. Thank you very much for opening our eyes.
Thank you.
I think we'll look into it more and more, possibly have a discussion with you, because
always happy to talk to you.
Yeah, component is not same all over, especially in the highly stressed conditions. We would have engineered something more to make sure that bad things won't occur. But I think we can do it much more, rigorously with more understanding, especially in the thresholds. Thank you so much, Dr. Sunder.
Thank you. Thank you.
Yeah, if I may ask another question. Sundar, you said something about the vacuum levels of 10⁻⁸ and above that, it may still react like air. So I had this question about if you had a fluctuating humidity or some sort of an environment versus when you have a controlled environment, just maybe mildly corrosive, but it's controlled. And when you have something which has a fluctuating humidity or corrosion level in air, just like how it happens naturally, is that something that will also affect your
your question, Jaya, brings my memory back to a PhD work which was done by Quinton Bowles in Delft University in the mid-70s. And what Quinton did was to grow a crack in high vacuum and then continue the test in air. And then go back to vacuum. And what he found, his deduction was not a direct deduction, but a very reliable one. Because, in air, striations will form. But in vacuum, striations don't form for various reasons. Okay. So he was amazed to find that when he switched from air to vacuum and continued the test at a pretty high K level, the striations continued to form for a while. And from that, what he deduced was, and that is what, we also thought was happening in our experiments, that this hydrogen, ionic hydrogen, which is released when a metal oxide is formed, it remains as such, and it basically chases the crack tip for a while because its surface diffuses. As you know, the mechanism of so-called hydrogen embrittlement is supposed to be through highly localized slip. By highly localizing the slip into one or a few planes, you're converting the fracture into a brittle fracture because you're not promoting yield in a uniform, on multiple planes. So if this is what happens, it probably addresses your question, right? That a fluctuating environment, it all depends on what is the period of that fluctuation.
Right. Yeah, I mean, like how you do fatigue loading at these different variable amplitudes. So I was wondering whether there is a need for testing with some sort of variable environment conditions. So.
Oh, okay. Well, if it all depends on what you're looking at. If you're looking at aircraft structures, the good news is the flight conditions are less damaging than the lab conditions in terms of environment. Because at altitude, you don't have the humidity levels that you have on the ground. And you raise a very important point, because these factors, they affect the near threshold behavior much more than they affect the behavior at higher growth rates.
Yeah.
In the Paris regime, even between air and vacuum, the difference will not be phenomenal.
Right.
But when you go further down, it's a huge difference. So, yeah.
Thank you. Yeah. Vikram, you're muted if you're trying to speak.
Any other questions from anybody? I don't see any hands raised. Okay. Well, I think we've. Oh, Dr. Sitaraman, did you want to ask again, or is that the old hand?
Old. Thank you.
Okay.
Dr. Sitaram is an old hand after all.
Thank you, Sunder. Thanks very much. Thanks for enlightening us, and we'll look forward to the more dedicated workshop at the December meeting.
Thank you for this opportunity, Vikram, Jaya, Deepa, wasn't able to come, I know, for this opportunity to present this talk. I look at every opportunity of talking about the new standard as a way of marketing it, not for any personal gain, but mainly to make sure that there is an awareness about the new test method and how it can affect work. So thank you very much.
Thank you, everyone. And
you want to say anything about next seminar or whatever?
We don't have an announcement about the next seminar, but there is going to be a workshop, like already mentioned in the beginning. Maybe not everybody had joined by then, but we'll send an announcement about this workshop that's happening in July, which is an ANRF pair workshop, I believe, where one of the things that they will talk about is going to be on this standard and many other things. That advertisement has been sent across to INSYS members as well as to LinkedIn. I don't have it handy here, sorry. And the abstract call for SIC is still open. June 21st is the last date for submissions for papers, and 31st July is when it is due for technical presentation. So I request those who are here to spread the word and submit abstracts for the same. Thank you.
Thank you.
Thank you, everybody. Bye.
Thank you all.
Bye. Thanks. Yeah.
Thank you.
Actually,